Okay, let's get started. Today's seminar speaker, we're happy to welcome our own Sasha Madronich, and he's been here since 1985, and he told me that he would have gotten out of here sooner, but it took him 30 years to do what should have taken 2 years. And I am cutting into his time, so I'm going to let him come up now.
That's about average, isn't it? Thank you, John, for that great and short introduction. It is a little bit long, so I apologize ahead of time. I'll try to speak faster. I got a speeding ticket on my way to the airport a few years ago, and I told the policeman, and he said, that I was going to the airport, late for the flight, and he said, don't worry, I'll ride faster. So really, this is a fulfilling request to talk about GECKO, to present GECKO more or less to the division, the hyper-explicit chemical model. And I am talking about it, but I really should recognize those people that have done most of the work. Our own here at NCAR, Julia, who I think is here someplace. And Alma could not be here this afternoon, but I think she's looking at it by video. And then Camille, who recently, where is Camille? There he is, who joined us in January. And of course, a long-term 20-year-old collaboration with the University of Paris with Bernard Amont. Bernard recently became an affiliate scientist of ACOM, so he'll be coming by even more often. And many of his students, I doubt that they have all of them listed here, but I just wanted to point out that Camille himself, that we stole from France, is from that pedigree. And of course, our funding agencies, NSF first of all, but also the Department of Energy, the Atmospheric Sciences Atmospheric Systems program has been supporting us for some time, as well as the French research agencies. So let me just jump into the fact that we have an enormous number of different hydrocarbons. That's really the first thing I want to get across here. And of course, biogenic hydrocarbons are by far the largest source of non-methane hydrocarbons. Methane is kind of a special case. But VOCs, or volatile organic compounds, or hydrocarbons, you see the biogenics are about 1,000 teragrams per year. And about half of that is isoprene. The 10-carbon terpenes account for another good slice of it. And then you have some sesquiterpenes with 15 carbon molecules, fairly large, complex molecules, as well as a number of oxygenated compounds, including some alcohols, acetone, and some fairly small aldehydes. Then, of course, you have anthropogenic hydrocarbons, which tend to be a little bit different. They are only about 10–15% of the global emission, but of course, locally, in a place like Mexico City, they are the dominant reactive VOCs there. And here you see some hydrocarbons measured by Eric Apple and his team from the C-130 during Milagro. And you see this row is just strictly alkanes. And then you have a whole bunch of ethenes down to here, and then a bunch of aromatic molecules. So again, a zoo, a real bestiary of different chemical species. And then you have the other big global source, fires. And here you see some recent results from the Missouri Fire Lab, where they burned various types of fuels. This one was a rice straw, and they measured the direct emissions of some 500 different VOCs from this, and published recently. I think John Orlando is a co-author of this paper. And you see, again, a whole bunch of different compounds arranged by families, and within each family, a whole bunch of substituted compounds. So this is really a fairly complicated picture, where you're even, just before you do any chemistry on them, you're starting with hundreds of precursor initial hydrocarbons. So I can't get into organic chemistry. I couldn't teach organic chemistry anyway, but in a few minutes, let me try to put a little bit of order into this, and basically by putting some family names for alkanes, some of the simplest hydrocarbons that have these either straight chains or branched chains. And of course, when they get longer, they can have many branches. And isomer is a different configuration. So butane, for example, with 4 carbons, have 2 different ways of arranging those. And then you have the double bond carbon species, like alkenes, like ethylene and propylene, like isoprene, which contains 2 double bonds, aromatics, which are, well, really have 2 resonant configurations, so they're sometimes written as a delocalized electron cloud, but basically double bonds. And then the terpenes also can have any number of double bonds. So this creates some special chemistry. So now, these hydrocarbons, hundreds of different ones, but they do follow a certain pattern of reactivity in the atmosphere, which we think we, at least in the crudest, roughest way, we understand. And that is, you can start with an initial hydrocarbon, RH, and the H is kind of shown explicitly because it will often react with something and be pulled off to make, for example, with OH, ozone, NO3, to make a radical. And then the red boxes are radical species, which have very short lifetimes. This radical is on the carbon. The carbon has an unpaired electron, and in tropospheric conditions, O2 adds immediately to make the peroxy radical, which then can make an alkoxy radical, and ultimately you make a carbonyl, like an aldehyde or a ketone. But you also have several side branches at high NOx, at low NOx, and I've shown a couple of them, but there are more. And so the side branches have their own chemistry. And once you form this first generation product, it can undergo fairly similar chemistry with OH, with ozone, with NO3. And now, since it's a little more complicated molecule, sometimes it can even photolyze or decompose thermally. So that's the general pattern. And eventually you end up and with the ultimate oxidation products, CO2 and water, if you ever get there. So that's a general picture. And I mentioned that very first reaction. Let me just spend a moment on the OH plus VOC reactions. OH is widely acknowledged as the cleaning agent of the atmosphere. So its reaction is really what starts this whole cascade of chemistry of the VOCs. And OH will have typically 2 reactions with VOCs. One is a simple abstraction where it pulls off a hydrogen atom, makes water, and leaves a carbon center radical here, the dot indicating the radical. This immediately adds O2 to make a peroxy radical. And by the way, this addition of O2 is the formation of potential ozone. Because what you have done here is you've taken double bonded O2, very strong double bond, and you've transformed it into a single bond. And so this extra oxygen is potential ozone. And you'll see from the chemistry later on. NO3 can also do some abstraction reactions. The other major OH reaction is addition to double bonds, where it adds to either one side or the other. This particular case is symmetric. And then this radical again adds O2 and makes future ozone. Now this radical that I just mentioned, you have the simple alkyl radicals where a bare carbon has, the radical is on the carbon. And as I mentioned, these are extremely reactive, will immediately add O2 to make peroxy radicals. And then later on, these will become alkoxies and then other radicals. I'm just introducing the names really here that form PAN-like compounds, and those that come from ozonolysis reactions of certain specific alkenes. So as you're doing all this chemistry, then those pure hydrocarbons get hydrogens pulled off and other things added on. And the type of things you can put on these things are listed here. You can make them into alcohols, and a few examples here: aldehydes, ketones, carboxylic acids, peroxides, peroxy acids, as well as nitrates. We heard some great talks in the last couple of weeks about organic nitrates, PAN-like compounds, and so on. And so really, if you now want to look in detail, not in general, but in detail at one single molecule, this is what the picture looks like. And this is an example for pentane plus OH. Here is your initial pentane. And you see pentane from the structure has 3 different carbon positions. So the reaction can happen in one of 3 different places: the terminal, second, or middle carbon. And what is shown here is just the reaction for the middle carbon. The other 2 are on different pages. So just this one pathway and pentane can make a whole bunch of radicals, and then these are the first non-radical products that come from these pathways, the ones in the brownish boxes. And so 1 generation deep, and you already have about a dozen stable products. Each one of these products can continue to react and have its own dozen or so products. So you see the growth can be really quite fantastic. And by comparison, what we do in our modeling can be much more limited. You have chemical mechanisms like in Seinfeld and Pandis in the textbook. They have about 10 reactions. So it's fun to play with and learn quite a bit about the general behavior of the system. But in typical air quality climate models, we have something on the order of 10 to 500 or so reactions. That's considered practically feasible in these models these days. And box models, well, there have been several. The master chemical mechanism has been extremely popular in the last few years. I'll show some comparisons. And they are in the order of 10 to the 4 reactions for hydrocarbons. And then there's the brute force approach, which is what I'm essentially showing to you. We're just going to try to do all of the reactions by hand, by machine, by whatever we can. So this is kind of a couple of points about the generator. Our objective in doing this is to retain the explicit chemical identity of all the molecules made by chemical transformations. And if we do that, that allows us then essentially to inventory everything about the system. The atomic composition, what functional groups are on there, the molecular structures, their rate constants and pathways, their thermodynamic properties like vapor pressure, hygroscopicity, Henry's law, as well as optical properties. So basically we know the molecules. That is a real advantage. We also would like to and insist on using lab data where it is available. In other words, we don't want the computer generation to invent reactions and calculate numbers for them when we actually know those reactions from lab measurements. The measurements get higher priority. But when the measurements are not available, then we use a number of structural activity relationships derived from mostly laboratory measurements of similar reactions to estimate the kinetics and the identity of the products. So that's the plan. And then we would like to go not 1 or 2 generations, but potentially all the way down to CO2 and water to see what all of the products along the way are. And also in doing that, we can apply systematic simplification methods and see how much difference they made. And of course, we could limit the mechanisms greatly by restricting to high NOx only or low NOx only, but we would like to stay general with respect to environmental conditions. So this is how the generator actually looks like. You have a VOC, which is written out, and the Fortran finger looks through the VOC, and it decides, according to some rules, first of all, is this molecule a radical, yes or not? That's the first decision. If it is a radical, if it's not a radical, let's start with that, then it will do, they will look for certain functional groups on the molecule, and if they're present, it will put that molecule through a subroutine that does reactions on it. And the reactions are kind of summarized graphically here. For example, in the case of OH, you have the possibility of the abstraction. I guess H2O should be shown here. or you can have addition to the double bond, like I was showing you earlier. You have similar reactions for ozone, NO3, photolysis has its own subtleties, and of course some molecules like PAN and its analogs can decompose thermally. If it's a radical, on the other hand, you have a whole bunch of different chemistry that you apply to it. I unfortunately don't have time to go through all of these details, but basically the peroxy radicals and the alkoxy radicals are really the critical things, because each one of them can potentially go in several different directions. And then after you make these products, these new products, you ask, are they really new or have they already existed? If they're new, then you send them back to the back of the queue waiting to react. And then you take the next one, VOC number 2. And you keep on doing that, refilling the stack until eventually the stack all gets emptied out by reaction, and then you're down to CO2 and water. But that's the basic idea. Now, I mentioned structure-activity relations, and these are really central because a lot of the molecules in GECKO have not been measured or even seen in the lab, looked for in the lab. And so an example of a structure-activity relations that comes from many dozens of papers of individual rate constant measurements reviewed in several studies. And in this case, for example, the abstraction of this hydrogen atom is given by a central rate constant and 2 multipliers that account for the identity of the nearest neighbor carbons. And depending on what those nearest neighbors are, then you multiply by a certain coefficient. And this is fairly simple, straightforward structure-activity rule, but remember, this is based on dozens and dozens of difficult experimental work. The other type of SAR that you can get is from, sometimes you can get it from measurements, but you can also get it sometimes from quantum chemical theory, and several groups, including the, I guess, Belgian or Dutch, help me. Belgian, thanks. Have been doing quantum chemical theory and finding sometimes equivalent or missing estimates that would not be otherwise available from measurements. And for alkoxy radicals in particular, which are a central branching point, there are in general 3 types of reactions, and it's interesting to recognize them because this one, reaction with O2, simply steals this hydrogen atom here to make HO2 and makes a nice simple ketone, and that's kind of a main path of degradation. But for some of them, and depending on specifically on the details of which alkoxy radical, you can also have a decomposition on the nearest carbon-carbon bond, so fragmentation into 2 smaller pieces. Or you can have a bite-back mechanism where this oxygen here essentially folds when the molecule is folded, because remember, these are really hexagonal bonds, you can steal a hydrogen from the other side, and then this will become a peroxy radical. And this type of reaction is critical because if you think of the formation of organic aerosols, for example, you can pretty much guess that fragmentation will not give you a lot of aerosols, but functionalization, making larger, stickier molecules, is likely to give you more organic aerosols. So the idea then is to go multiple generations. This is kind of a summary where you start with VOC, you do the first generation chemistry, you make a new VOC or a whole bunch of new VOCs, they go to the next generation, and so on. The mechanisms get large. You should not be surprised. Here is the number of reactions or species. By the way, the number of reactions is typically 5 times the number of species. This is the rule of thumb. The number of reactions for different size alkanes, propane, butane, and so on, the black curve. Isoprene is here. So for isoprene, you need about 8,000 chemical species and about 30,000 reactions. And notice that it increases by a factor of 10 for every carbon atom. So if you want to go C15, C20, you are in some very, very large numbers. And you can kind of understand this intuitively in a very simple odometer-like model. If you have a string of 12 carbons, each one has a position that it can flip through. And if you remember a few slides back, I showed you all the functional groups, alcohols, ketones. Well, on a terminal carbon, you can put 11 different functional groups, according to standard chemistry. On an internal one, 7. So you have 11 squared permutations here, and then the number of carbon minus the 2 terminals permutations here. And you can get a pretty good estimate by taking this product, maybe 1/2 to account for symmetry, and sum over all the fragments, not just the full length, but also all the fragments that can be made from it. And you get that straight line. When you actually run GECKO, you get values for alkanes that approach this straight line reasonably well, but they're fortunately a little bit lower. We'll be very confused if they were higher than that. But ultimately, even this, we understand this growth, but even this growth in GECKO is completely unsustainable and not really usable in current day computing. So what we looked for, even in GECKO, there are some pretty strong simplifications. And one of them is that if something is 5 or 6 generations deep, and it looks very similar, same mass, same more or less structure or something else, we tend to, at some point, deep down, lump things together. That makes quite a bit of difference. But the other thing that makes a huge difference is if we set a threshold of 10 to the minus 13 atmospheres, so a tenth of a ppt, for the vapor, for things that have vapor pressures lower than that. The point is that if they have such low vapor pressures, then they will almost immediately partition to aerosols, and they will not then longer be taking part in gas phase chemistry. So we can keep them, but remove them from the gas phase. And if we do that, then we get a much more reasonable growth curve. And in fact, at some point, it even turns over, because the very long carbon molecules only need to go 1 generation or so before becoming so sticky they condense. So this has really made it feasible, rather than being on this line that has this outrageous growth. So here are some early results. I think 2007, we took 1 octene, we let it react under constant light. And this is just to give you some idea of how the mechanism works. Here's 1 octene, the dashed line, and you see it decreases very rapidly here. And it's making lots of CO and CO2, pretty much irreversibly, but it's also making these secondary organics. Let's look at what, next plot, the total secondary organics are. So the black curve is the same here. And this total secondary organics are, a lot of it is gas phase with a strong time variability and a slower buildup and decay of particulate organics. And if you take the particulate organics and break them down some more, you can see that most of them still have the 8 carbon chain of the original octene still intact in the particle phase. But you also have some contribution from smaller fragments. And if you take these C8 compounds and break them down, you find that the majority of them have 4 or 5 functional groups, hydroxy, ketone, nitrate, and so on. And things with fewer functional groups are just not going onto the aerosols. So it's kind of an overall mass budget picture. Now, of course, we can also interrogate the results to see the detailed chemical composition. With so many chemicals, it's not convenient to plot individual molecules, but we can sum up all the alcohols and ketones in the particle and see how much they contribute. And remember, you need 4 or 5 of them on every molecule on average. The other thing that comes out here is that the yield of aerosols you make is not necessarily a simple constant. It depends, among other things, several things, but it also depends on the NOx and the hydrocarbon conditions, somewhat resembling an ECMA diagram where you have a maximum formation along a ridgeline. Now, the other thing we can do, because we know the explicit molecules, is we can try to estimate their vapor pressures. Actually, we have to do that if we want to see what fraction goes onto aerosol particles. And there are a number of ways to do that. They are not all the same. They give you different results. Here you see two methods being compared. And for smaller, not very functionalized molecule, they're in pretty good agreement. But for things with 4 functional groups, notice the logarithmic base 10 scales here, 5 orders of magnitude uncertainty. So that's an issue. Fortunately, we're not too worried about these extremely low vapor pressures because they condense either with 100% certainty or 99.999% certainty. But it's really these intermediates that are contribute to the uncertainty of the whole subject, really. Now, if you look at typical evolution in GECKO for various size molecules, here's 8 carbon, 16, and 24 straight alkane straight chain. And here, in any one column here, this is time. So initial, 1 day, 2 days, 3 days, or 5 days. And you see this is the initial compound, and it's plotted on a graph that has vapor pressure, or C star, as some people have come to call it, which is an equivalent aerosol mass concentration. But think of it as vapor pressure. And so this is your initial octane. And after 1 day, you see it has made a bunch of products. The red ones, the gray ones conserve the chain length. So the gray ones here have 8 carbons, here they have 16 carbons. The red points are fragments, smaller than the precursor. And so you see you have some fragmentation, but by and large things are getting towards a lower vapor pressure, so stickier, but they're not quite reaching this 10 micrograms per cubic meter, which is where they would have to be in order to be of practical importance. In other words, this is a typical value measured in the real atmosphere. So if they are to the right of this line, they are in the gas phase. To the left of this line, approximately, they're in the particle phase. And if you're familiar with the aerosol mass spectrometer, they often report their aerosol measurements as highly oxidized or not highly oxidized. And people often make the association that this HOA, not highly oxidized, is equivalent to primary organic aerosols. Well, maybe not. So if you start with a bigger molecule, you see you now have more aerosol products, more fragments as well, but you end up with much more to the left of the partitioning line here after several days. If you start with a very large molecule, you see you're almost condensing the original material. But as you react, you make all these products. And what is interesting is that these products would have an oxidation state that is still quite low, and AMS may or may not assign that correctly to secondary organic aerosol. It may be assigning it to primary organic aerosol by mistake. So that's. Now, we've also done, in fact, Bernard very recently did some beautiful comparisons with the master chemical mechanism. This is not so simple because to do a good comparison, you need to make sure all the other conditions are really treated in the same way. So to get 2 models to run for exactly the same situation is a little bit of work. But you see in the gas phase, the GECKO and MCM really are in pretty good agreement with some subtle differences in this middle size range here. But the big difference is in the particle phase, where GECKO makes much, much more aerosol than MCM. And you can see that graphically, again, as a function of vapor pressure, and in this case, as a function of Henry's law coefficient solubility. You see GECKO has products that extend all the way up into this diagram, while MCM is much more limited. Now, this is one model against another model, but of course, nobody should believe that. The gold standard, if I may quote John Seinfeld, for SOA formation has been smog chambers. And we, in our initial simulations, found that GECKO, the red points here, systematically overestimated yields measured in smog chambers. And by the way, each point is one molecule here in this linear series. These are the measurements. This is the GECKO. And you see in for cyclic, branched, various alkenes and alkanes, GECKO seems to be a little bit high. Stephanie La, but I think also Xuan Zheng and others have done very similar work, showing that in chambers you have a problem of losing not so much the particles to the walls, but the gases to the walls. Those are the gases that are in equilibrium with the particles. So by losing the gases to the walls, you tend to evaporate the particles, or at least they don't get as big as they should. And so after this correction is made and applied through GECKO, then you see the red points become the purple points. And now all of a sudden, GECKO is starting to look really fairly reasonable with smog chamber experiments. Okay, then we tried to go outside. This is Mexico City. We were there in 2006 making measurements. Actually, I remember taking this picture. We're flying in from the south, and you see the wall of the city pollution ahead of us. Downtown is under here someplace. And so the problem has been for SOA organic particles in particular that the models have been doing very, very badly, underestimating the mass loading of aerosols, secondary aerosols, by factors, 3 factors of 10 or so. And these are 3 different locations in Mexico City. Obviously, these are the measurements, and these are 2 different models. Julia did some wonderful box modeling for Mexico City with a whole bunch of hydrocarbons. In fact, these are the same ones you saw earlier from Eric's work. And well, first to look at the gas phase species, we managed to do fairly well. Our boundary layer seems to be a little too small at night. The model is over-predicting the nighttime values. But then during the day, it seems pretty good for OH, for HO2, which is the solid curve with the black points. And this is HO2 plus RO2 with a fairly typical afternoon sunset peak in RO2 that I see in the model all the time, and I've never seen in the measurements, but that's another story. So then we tried to calculate the primary organic aerosol and the secondary organic aerosols, and well, this is the result. I will say that probably this is a little luckier than it deserves to be. For example, there is an element of modern carbon, which is not in our model, which we know is part of the SOA budget. So the green is a little bit fortuitous, but certainly I think much better than the previous VBS type models. We can unravel the top 20 molecules without too much problem, just print them out. And we know roughly where they come from. We know their vapor pressures and so on. It's a lot to read through, obviously, but the main thing I want to point out is it's mostly from two precursors, light aromatics like benzene, toluene, xylenes, and from large alkanes, C15 to C25 alkanes. And you can see, you can look through here, you have all sorts of ranges of oxygenation and nitrogenation. In fact, some of the this is now a breakdown of the aerosol mass by functional groups. And if you look here, at this point in time, you see that a majority contain hydroxy ketones and nitrates, large amounts of those, as well as a bunch from aromatics. But these are, of course, summed over the families. We also looked a little bit about what happens to the plume as it goes out. And one surprising result, well, okay, we took the urban plume, which you see here, and then at the end of day 1, we released it like a Lagrangian air parcel, let it float away. And sure enough, its concentration of aerosol goes down. We also added a dilution with clean air, and so part of the reason the concentration goes down is simply because of dilution. But if we now take the total mass across the plume, in other words, numerically undiluted, then we find that over the course of a few days, the total aerosol mass continues to increase by a factor of 3, 4, 5. We recently traced this down to a few molecules that I don't want to say too much yet because we're still looking at it, but it's either an artifact of the model or it's something that is telling us go look for these specific molecules. But this is really quite surprising because from an air quality point of view, you can think of the plume as it's being diluted as being cleaner and then nicer. But from a radiative forcing point of view, it's just getting worse. So we really need to get to the bottom of this and really understand whether there is, as this is suggesting, a lot of SOA growth downwind of a city that is not accounted for if you just look in the city. The other thing we can do from this is now develop a full spectrum, a distribution of vapor pressures for the particles, for the gases. And you see here for the Mexico City outflow, day 1, it's the red curve. And you see that, there is not very much in the low vapor pressure regime. But this, if you look here, is actually the 1-to-1 line. So anything above this line is going to be actively seeding the formation of the aerosols. In other words, this part of the vapor pressure curve causes self-seeding of the growth of the aerosols in the city. And then this growth continues from day to day, and you see it growing at the lower vapor pressure, and you see it being depressed in the mid-range here. Now, so far I've been talking about the production of aerosols. Let me say in the last few minutes a couple of words about the removal of aerosols. And one of the fundamental principles is that the amount in the atmosphere depends equally on the formation and the removal. You can't escape that. Now, the removal may be chemical, maybe ventilation or what, but you have to know the removal if you want to predict the atmospheric amount. And remarkably, if you look at the literature, most of the studies on organic aerosols have been done on the formation side, very little on the removal side. If you take global models, this is from a recent intercomparison of global models, and you look at what is done there for organic aerosols, 85% is removed by wet deposition, rain out. And some 15% of the aerosol is removed by dry deposition. Well, we thought we could look a little bit more detail because deposition is very sensitive to these molecular thermodynamic parameters like Henry's law and vapor pressure. And so, for example, for wet deposition, it's a direct exchange between the gas and the droplet phase, the raindrop. For dry deposition, the very final step where the gas diffuses and reacts in the stomata of the plants, that is also dependent on the solubility, the Henry's law coefficient. So Alma took GECKO results and plotted them, vapor pressure, or C star, against Henry's law coefficient calculated in the model, and made fits for all the molecules under various conditions of these curves. And so for every vapor pressure, she was able to assign a solubility number. Now, if you then take those correlations and you put them in a 3D model like WRF-Chem, you can improve the representation of wet and dry deposition of the gases and the particles. And what she found was, I thought, very interesting that, remember, in the global models, 85% of the loss was wet deposition of particles. Here, we're estimating only about 28% is by that process. Most of the loss is by dry deposition of the gases, which then cause the particle to evaporate to readjust the equilibrium, just like the wall effects in the small chambers. And so basically the same principle that makes a huge difference in the atmosphere. Another removal question that we posed was about photolytic removal. If you look at some literature, you find that a lot of reported organic aerosols show significant spectral absorption, typically increasing toward UV, shorter UV wavelengths. Here is the mass absorption coefficient meter square per gram for soot. So most organic aerosols are well below soot by a factor of 10 or so, but their abundance is about 10 times that of soot. So there is a real question as to how much light is absorbed by these organic aerosols, which have a name, by the way, brown carbon. That's what brown carbon is. So the other question is, could the UV light break some of these molecules? And so we did a sensitivity study with GECKO for one special case here. And the first calculation without organic photolysis, there is inorganic other photolysis, but without any detailed organic photolysis would predict this much. If we now allow gas phase photolysis to happen to the organics, and this is fairly reliable, we think we have good numbers for this, then you get quite a bit less. But remember, a lot of the stickier, more photoactive particles have condensed in the particles. What are they doing in the particles? The standard assumption is that once a molecule is in the particle, it is protected from photolysis, it's protected from OH reaction. That's probably not true. And so if we made an assumption that the molecules continue to photolyze with their gas phase photolysis rate, then you would have this gold curve. And if in addition, or separately, I should say, we make a very speculative assumption, taking a mass absorption coefficient of 0.1 from the previous plot, and let's say that for every 100 photons, UV photons that are absorbed, you kick out one carbon atom. That's the smallest piece you could possibly kick out. Well, hydrogen, but okay. If that quantum yield is 1%, and you take this mass absorption coefficient, then you get that the photolysis lifetime or photolysis rate coefficient for SOA is about 4 times 10 to the minus 4 of the JNO2 value. That seems like a small number, but it has big consequences. So this is a global model simulation that Alma did again, with putting in some of these numbers, and that's the loss, percentage loss in SOA at, I'm sorry, I think this is surface or near the surface, with that assumed photolysis coefficient. You see that near the sources, you're losing 20, 30%. Far away from the sources where sunlight has been acting on it, you lose 80, 90% of the SOA if this mechanism is operative. And if you look at some vertical profiles, but there are many to look at, I wouldn't base it on just a few, but these are the black is the observations, and the model with enhanced particle photolysis is here. Here it's not obvious that it's doing better, but here it is suggestive that it's doing better. So maybe there's some improvement. But in any case, it's a proposed process that really needs to be studied because the potential effects, if this is happening, are completely changing the budget of the SOA. So to summarize a little bit what Alma has been doing by putting some of the GECKO parameterizations into the 3D models is that, we used to think that organic particle loss was almost entirely by wet deposition. And what we're finding globally is that actually the largest organic sink is the dry deposition of the gases, which is in equilibrium with the particles. The particles don't deposit very rapid dry deposit because they're heavy, of course. They're limited by their ability to diffuse. But wet deposition, dry deposition of the gases is important, as is potential chemical, photolytic, or other heterogeneous loss. So let me summarize a little bit. There are so many things to be done still. And I could start just with the gas phase chemistry, which is, of course, where GECKO is focused. I think the development and structure activity relationships is extremely important to make GECKO successful. But it also can go the other way, where GECKO can suggest, recommend things that should be started in the lab to to get to those structure-activity relations that are needed most efficiently. Right now, we're doing very little, almost nothing with in-particle chemistry. We know what happens in the lab. There is a number of different processes that can happen. Particle chemistry needs to be added in. Camille has started working on cloud phase chemistry already, and I'm sure we'll be making some progress in the next year or two on that. That is a really interesting topic that I know nothing about, and so I'm not going to say much, but I just remember James Smith showing me some results about how nucleation in the smallest particle, organic acids, are most abundant, but as the particles become bigger, the acids are less abundant, and other things like ketones and alcohols come in, which has a lot of implications for the chemistry of new particle formation. There is a possibility of surface reactions. There are some groups looking at that. And also, you probably heard that they're not necessarily nice liquid particles. Some of them may be viscous, glassy, and that, of course, changes the partitioning between the gas phase and the particle phase and so on. So it's a complicated problem. We have some largish ongoing activities. I'm sure I could put more here, but some that are worth being aware of is we have a DOE grant that Camille is working with to specifically look at 3 field campaigns, and in the context of 3 individual topics: the biogenic anthropogenic interface downwind of Manaus in the Amazon, where we get air from the city or from the forest, a brown carbon biomass burning observational program that was done a couple of years ago in the western US, and a field campaign that just finished a few months ago looking at clouds over South Great Plains in Oklahoma with lots of in-cloud and out-of-cloud measurements of organics. That should be really interesting. There's a lot of activity in Europe by Bernard Dumont and Andrew Ricard and the MCM group, basically. They're starting to work together to integrate, and I think that would be a very, very useful activity. And of course, here within ACOM, we've been talking more and more about the reactive carbon initiative and how we can perhaps use GECKO as a repository and a test bed for some of the data that comes from chambers and labs. And also, I think we need to go out in the field. Carbon closure is still an open question. So just to summarize, a final thought about why all the complexity. Sometimes I get frustrated, and sometimes I think I understand why. Not sure, but even GECKO is not really that complicated. GECKO is a lot of repeated simplicity, and if you repeat chemical simplicity enough, you're going to end up with some really pretty polymers. But the real diversity is a whole other story, and I don't think GECKO is maybe a little step in that direction, but still a long ways from it. So, thank you. Questions?
One of the unanswered questions as of fairly recently was why particle nucleation, gas to particle conversion was rarely seen in the Amazon, and you talked about some work with the Go Amazon project. So is there any information you've learned based on that mixture of organics and oxidants that
honestly, we just started the project, so we don't really have simulations for that. But what I've heard is that it may be related to particles being formed aloft and then being ventilated down. That was a topic of discussion a few months ago at a meeting. Yeah, sorry. Here. If you take a mass absorption coefficient of this mass absorption, and a quantum yield of 1% across the UV spectrum, so anything shorter than 400 nanometers is given a quantum yield of 1% to eject one carbon atom. With those two, I can calculate a photolysis coefficient, and I can compare it to JNO2, and it turns out to be 0.04% of JNO2 numerically. It's not by design, it's just, if I put in these two numbers, that's what I get.
And then you're using the same light sensitivity as for NO2?
It's almost the same. NO2 has a maximum around 360 or so, and really falls off around 330. Here I'm saying constant quantum yield for every photon in the UV. So it's really flatter than the NO2. But it's an order of magnitude estimate. You know, it's not meant to be 20%. This is really factor of 3 at best. We don't even know. However, you know, these quantum yields in liquid phase are not ridiculous, because these are the type of quantum yields, for example, measured for Norrish type 1 and Norrish type 2 photolysis of aldehydes in solution, not just in the gas phase.
And then you say it cuts a big molecule in half and then one out.
We are making the crude assumption that it kicks out one carbon atom as a minimum step to do something. Okay, it could kick out a hydrogen atom, but that's silly. It could come out as carbon monoxide, it could come out as CO2, formaldehyde. In fact, Sergei Niskorodov at Irvine has done a number of lab experiments, and depending on how you make the SOA, they will or will not photolyze. For example, SOA made from limonene photolyzes almost to completion within an hour. And other, I think from aromatics, they don't seem to photolyze, but that's still an open question. So that's, I'll admit it, it's very speculative. We just don't have the numbers. On the other hand, the good news is if this is the major photolysis, if photolysis is the major loss for aerosols, after we work out some of these details from the lab, it's a lot easier to model photolysis in global models than to model precipitation. So,
yeah, Sasha, you showed how, with all this different structures, we can get estimates of the Henry's law and volatility and things. Could you comment on how GECKO-A being used or will be used to either guide or exercise our view on volatility basis sets, VBS, no type of things?
Well, look, the volatility basis set basically says we have a whole bunch of different organic molecules, but we're going to retain one piece of information about them, their vapor pressure. And everything will be binned into boxes according to vapor pressure. More than that, you know nothing. What we are saying is that for a given vapor pressure, there is a certain Henry's law coefficient. There may be a certain absorption coefficient. There could be. So in that sense, we are helping to fill the other dimensions of the volatility basis set. Volatility basis set is just one dimension. We can fill the other dimension. Is that your question? I'm not sure.
Yeah, kind of, yeah. Just how are you extending VBS or getting rid of it altogether or whatever?
Well, if you go, in fact, okay, this is, but Jim Pankow wrote a nice paper a couple of years ago in which he discussed the anonymized view of SOA formation versus the molecular view. And he gave the VBS as an example of the anonymized view. And what he's saying with that hard word to pronounce is that only one piece of information is being retained about the molecule. And the molecular view, you can retain whatever you need. So here are typical VBS bins. Okay? And normally you just know, well, maybe I have so much material in this bin. But now you know that this material also has this Henry's law coefficient. So that's just two-dimensional now, but of course with GECKO you can do whatever axis you want.
So for the non-expert, I'm surprised to see such a big difference between GECKO and the master chemical mechanism. So can you explain that, why that is, and which is better, or should we have different other models, or?
Well, the master chemical mechanism is great. It's about 17,000 reactions. I don't remember how many species, but probably a factor of 5 less. It was written by hand. And I used to write mechanisms by hand also, and I remember a couple of things. When I was working with Jack Albert, I would come up with this very complicated molecule and think, oh, should I keep on degrading it? And I would ask Jack, and he, back then we were interested in ozone and acid rain. His answer was, oh, no, don't worry about it, just gonna go into aerosols. Well, now we're interested in that, okay. MCM is very good for ozone. And we've done a lot of detailed comparisons in the gas phase, and they really agree quite well. I had one comparison here. Yeah, here. This for one system. I have graphs for other ones if you want to see. But you see, the overall features are similar. But notice how it's missing. MCM is missing a lot of the intermediate stuff. And that's because it just doesn't have the same amount of detail. And when you plot it out as points, you can see a spread of points here that just isn't. MCM tends to have a few molecules with large concentrations. They both conserve mass approximately. So that's not the point. The point is that this has much more diversification. The consequences for the gas phase chemistry are not very much. In fact, if you calculate ozone, it's almost identical between the MCM, and that's in the 2005 paper. For the particles, because of this difference here, you have very different results. Which is right? Well, we did the testing against small chambers and it seems okay. That's not to say that MCM is wrong, because we happen to be in good agreement with chambers. They may do well for this case too. So, okay.
So another question from very much a non-expert. With regards to sort of the last point about the complexity issue, I wondered if you could say a little bit more about that. I guess in terms of whether there are particular problems where you see this kind of complexity being irreducible, and we're really going to need to understand all of the gory details to get a final answer about, some air quality question or radiative forcing? Or do you think that once you really do understand all the pathways, you will be able to reduce things down to parameterizations that can go into global models to understand sort of global impacts of all the complexities of this organic chemistry?
This is a case where I'm going to answer the question I wish you had asked. First of all, that last plot was intended more or less metaphorically, not too literally, But so if we were trying to model biology, then I think that would become very, very relevant, that complexity issue. The fact that you have biology putting hydrocarbons into the atmosphere is what creates all the variety, whether it's fossilized biology or whether it's modern biology. It's all from the same place. But does diversity remain important in the atmosphere? That's one of the things that GECKO can look at, but probably not as much as it would if you're trying to predict genetics. So I don't think in the atmosphere you have a little more mixing and randomizing that helps. Another issue is, and the concern has been raised, is whether by adding all these estimates of reactions, you're just bringing in noise into the model, and whether this noise is accumulating so that by the time you finish all the details, your result is totally meaningless. I don't have a good answer for that. I think we could do some testing for that, But my gut feeling is that these tend to be dissipative reactions, a lot of them. So these uncertainties and errors don't tend to build on each other, but rather they tend to dampen away. That's my gut feeling. The other gut feeling I have is that it's probably better than setting every rate constant to exactly 0, which is what you do if you don't do this. So I suspect we're learning something from this. The third point I want to make is that rather than looking at all of the details of every one of 1,000 million reactions, this allows us to kind of sit back and look at the emerging properties of the whole system rather than us wasting all the time in being lost in the detail. So looking at emerging properties, and that plot of Henry's law versus vapor pressure is an emerging property that is being used well beyond this model itself. So, I'm around if you have more questions. And if you would like to use GECKO. One of the things that we are seriously debating is how to make GECKO more usable by the community. There are a lot of problems that it could dig into, and we just don't have enough people to do all the problems, to do all the possible applications. But we do want to maintain some type of coherence and not have a whole diversification of models. So, thanks.
Okay, well, thanks again.